Assalamualaikum guys. So this is the part 3 of measurement of physical quantities, and in this video we will look at the homogeneity test and homogeneous equations. If you haven't seen the last two videos, I'll leave the link in the description box below to watch them out before basically going into this session. So what do we mean by a homogeneous equation or homogeneity test? So basically, if an equation has the same units on both sides, then the equation is said to be homogeneous and it is considered to be the correct equation. So let's look at an example, which is S is equal to ut. Over here, S is the displacement, which is basically measured in meters, and u is the velocity measured in meters per second, and t is the time in seconds. Now, how do I know that this is the correct equation in the world of physics? Just do the homogeneity test. So we have meters on the left hand side and meters on the right hand side as well, because meters per second into seconds are going to get cancelled out, and so you have meters on both sides. This tells me this is a homogeneous equation. This is the correct equation. So I hope you have an idea of what the homogeneity test is by now, and by this simple example. If not, well, we are here to practice many more questions and hopefully it will start making sense. So first problem, what if someone comes up to you and tells you, well, S is equal to ut square plus half at, at is the correct equation in the world of physics. Now, how you as a physicist and a student of A-level physics can tell them whether they're right or wrong? Well, just do the homogeneity test. So S being displacement is measured in meters. So the left hand side, units of the equation are meters. For the right hand side, U is measured in meters per second, and time, squares into second square plus half, and then acceleration is measured in meters per second square, and then you have time, which is measured in seconds. Now we can simply cancel those seconds out in order to simplify the equation, and what we basically would be left off with is meter second plus half meter per second. Now you can clearly see that this is not the correct equation, or these are not the correct bases or the correct base units on the right hand side. They don't, they're not coherent with meters on the left hand side. You can get rid of that half because that's just a constant and we are interested in the base units alone. So meters on the left hand side, meter second plus meter per second, exactly, you can clearly see they're not equal to one another. So this means this equation is not correct. The homogeneity test tells us that this is not the correct version, at least, of this equation. So what is then? All right, so this exactly, the previous slide showed us the incorrect version of this equation. The correct equation is S is equal to ut plus half at square, which is an equation of linear motion. We will dive more into it when we do the chapter of kinematics, but as of here we know that S is the displacement measured in meters, u is the velocity measured in meters per second, time is just seconds, plus 1 over half. Now if you want, you can consider the half. If you want, you can ignore it. I'll give both the cases, but considering the half, you get meters per second square for acceleration and second square for time. Now again, you cancel out the units and you see you're left with meters, and then meters plus meter half. Now take the LCM, and once you take the LCM, you get 2m over 2, and that's going to get cancelled out, and you're left with meters on the right hand side. You can clearly see you have meters on the left hand side, meters on the right hand side. So this means this is the correct equation in the world of physics, right? I think, and I guess, and I hope it's fascinating for all of you. Now, what happens if I do not consider that 1 over half? Now, trust me, you don't need to consider any constants, any numbers as you do this, because at the end of the day, it's the units we're focused on. If you do consider if you do not consider the 1 over half, you get your answer as m is equal to 2m, and in this case, you can ignore the 2 in the final answer. So either you ignore the constants initially or you ignore the constants at the end. It doesn't matter, because what we're focused on is the units. Now let's look at another problem. So they've given you the speed of a waterway, which is given by this formula where P stands for pressure, rho stands for density, and gamma is a constant which does not carry any unit. And so there are three parts to it. The first one says, what is the SI base unit of pressure? Now, if you've seen the last video or the last lesson on this chapter, you will know how to figure this out. Just take any equation which has pressure in it. I'll take P is equal to F over A. Now F, we did that SI in SI units, it is kg meter per second square, and area is meter square. So when I simplify that up, the SI base units of pressure are kg per meter per second square. All right, and similarly you can also do the second part, which is what is the SI unit of density. Density is mass over volume. Your mass is measured in kg and your volume in SI units is measured in cubic meters. So now just bring the cubic meters above if you want. It will be kg per cubic meters. So A and B are done. The C is using the homogeneity idea shows that gamma is a constant which does not carry any unit. So for this, what I will do is, we know v is the velocity, so it is measured in meters per second, which is equal to the under root of gamma, and then plugging the SI units of pressure and density there. Now notice how there's a square root. Now we can get rid of it by simply squaring both of those sides, and that's what I will do. So we're left with meter square per second square, and gamma remains as it is, and the other units also remain as it is. So I'll write that down. Now I can basically get rid of the kgs, alright, and I can bring that cubic meters above. I hope you remember that whenever you bring a denominator into the numerator, you basically have to switch the sign of the power. So that's why when I bring meter raised to the power minus in the numerator, it gets meter square. And so simplifying this up, I hope you know indexes, and you get gamma into meter meter square into second square. And once you have that down, you can clearly see that meter square per second square and same is on the right hand side. These two are the same units, they're going to get cancelled out, and so gamma is just equal to 1. Now gamma is equal to 1, so this means it is a constant indeed. It is not equal to some variable, it is equal to some numbers. So even in this case, and secondly, it does not have any units either. You can clearly see it's just 1. Now if you have like something like e or pi, well, these are also constants, you can also have them in, but the point is we do not have any variables in the gamma, so this means it is a constant indeed, it's equal to some number. Now let's do problem number 3, which says that I is equal to nqavk, and simply they're asking you, well, what value of k for this makes this the correct equation. So I is the current measured in amperes, it's written in the question above. N is the number of electrons per unit volume. Number of electrons is just going to be some constant like 60, 70, 80, so I'm just going to ignore that, there are no units there, but it's per cubic unit volume, so I have to consider per unit volume units. Then Q is the charge, and we have already done that coulombs in SI base units is ampere second. Then A is the cross sectional area measured in meters square, and V is the velocity measured in meters per second, which is raised to the power of k, and we are to find that out. So if on the left hand side I have ampere as my unit, then on the right hand side I should also have the same unit, that is I should also have amperes in order for this to be the correct equation. So the goal is to get ampere on the right hand side, remember that. So we have per meter cube ampere into second into meter square. Now meter square and cubic per cubic meters, they can actually get cancelled out using indexes. I'm actually left with meter raised to the power of -1 ampere into second, and then I have meter per second and then raised to the power of k. Now notice how all of this together is like the same thing, they're actually cancelling each other out, because if I write all of this in the conventional way, what I would be left with is basically meters second per meter into ampere into meter per second raised to the power of k. Now that might not make a lot of sense right now, but let's look into it. So if you basically write this instead of an index form in your conventional form, you have second, alright, you have second per meter into ampere into meter per second raised to the power of k. Now notice if k is just equal to 1, even then meter is going to cancel out meter, second will cancel out second, and we will be left with ampere. So this means k is just going to be 1. This is, trust me, this is just a trial and error question. When you're at this stage, it's just trial and error. You can clearly see that the units are cancelling each other out when k is equal to 1. So you have ampere on the right hand side, and that's the correct format. So in the next video, we will do the estimation of physical quantities and standards and prefixes. I hope you found this video helpful, and in order to access our PDF notes in this presentation, visit our blog. If you need more information about our ongoing sessions, you can visit our Instagram page as well, or book a session for yourself. And until the next time, Khuda Hafiz. Hope you enjoyed.